Hello everyone, my name is Siim Heinsalu from Utaka Laboratory, Waseda University. It gives me great pleasure to make a presentation regarding optimization of suspended ladder Bragg grating silicon sensors for high wavelength or amplitude sensitivity. The requirements for current sensors would be high sensitivity, small cost, and small size. Ladder Q are perfectly satisfied with the silicon insulator platform. So the goal in this work was enhance the sensor based on the requirements. Now the sensitivity, we have two options. Either we look the wavelength shift or the amplitude change after measuring by different mediums. With this SOI platform, of course, we will have various resonant devices such as the Matsushima interferometer, microring resonator, or Bragg grating. With the Matsushima interferometer, we have two large footprints typically. With microring resonator, we would have the bending ones. So we selected the Bragg grating where the typical spectrum is as such. Now to increase the sensitivity of the Bragg grating, we can modify the waveguide shape itself, whereby the changing to the medium would be higher. We also tried to do this approach by selecting the sub-alternating slot case with multiple slots. And then after rigorous optimization, we obtained up to 730 nanometers per RIU. Further to increase the sensitivity, we suspended the consideration, and after optimization, we obtained 1100 nanometers per RIU. Of course, we can have the plasmonic materials also. Increases the cost. Now, these two options are rather complex, many parameters. Thus, optimization is quite long. To reduce the time, we can reduce the complexity by reducing the parameters. And in this case, we have the suspended ladder Bragg grating. To have this high wavelength sensitivity with this suspended ladder Bragg grating, we considered various parameters where the ratio was most efficient. Reducing the ratio in simulation, we obtained 1100 nanometers per RIU. But in experiment, 865, and both cases were quite compact, around 11 micrometers. The decrease comes at the cost of increasing the transmission loss, of course, also. The secondary approach, high amplitude sensitivity, was obtained by considering the T10 and T20 stop bands and to have the stop band edge combination perfectly matched, whereby we would have this sharp peak. Rough parameters for this consideration can be obtained by the 2D FTE of delta NF mapping and more precise parameters with 3D FTTD. Of this optimal consideration, we can increase the end count to which the slope increases. This also we verified experimentally, where the both simulation and experimental results were better than the previous best result. Thank you for attention. I'd like to hear the questions if you have.